Okay, here we have a very classic tension problem utilizing vectors, and the precept of this problem is that over here on the left we have a crane, and over here on the right we have a crane, and together through cables, those two are supporting our 24,240 pound weight in a state of equilibrium. So it's not moving left, not moving right, not moving up, not moving down. They have so kindly given us some angles. Sometimes we have to work a little bit for those angles, and they'll give us, for instance, lengths of cables and some other length values, and we may have to do a little bit of SOHCAHTOA work to come up with those angles. But those are pretty important for us. Okay, so what we're dealing with here is we have a vector. In other words, this cable there's a tension on it, and it is pulling up and to the left, while this vector is pulling up and to the right. It has a tension on it we'll call T2. And while they are not pulling left and up independently. T1 is does have a left component to its tension and a vertical component to its tension, while T1 has a right component and an up component to its tension. So we want to start talking about those. So if we look at T1, there is a pull in this direction. And I would like to talk about that component of our vector, that horizontal component, in terms of T1. So I'm going to go ahead and just sort of complete this rectangle, and I'm interested, and I'm going to temporarily call this value X down here. And that means from the 24.3, I'd like to talk about the hypotenuse. I'm interested in the adjacent, so of course cosine will get the job done for us. 24.3 is adjacent X on T1. Or that horizontal component X, if I multiply both sides of that by T1, can be stated as T1 cosine 24.3. And likewise, there's a horizontal component pulling to the right on T2. And to talk about it, if I temporarily call it X, then I could say that it is also cosine 44.5 is adjacent X on T2, making this guy's horizontal component, solve not T squared, T2, making this guy's horizontal component, if I multiply both sides by T2 cosine 44.5. Now, what do we know about their horizontal components? If this weight is in a state of equilibrium, then we must be pulling just as hard to the left as we are to the right, so these two values should be equal. And I'm going to represent that in this form. T1 cosine 24.3 minus T2 cosine 44.5 is 0. They're canceling each other out. Okay, we'll come back to that. You'll see why I wrote it in that form shortly. Let's talk about the vertical component. Let's temporarily call on our tension 1, our crane 1, let's temporarily call this Y. And now I'd like to talk about that in terms of T1. So from 24.3, I'm now talking about Y, my opposite. I'm interested in utilizing my hypotenuse. That, of course, is sine. So we get sine of 24.3 equals Y on T1. Or our Y value, once again I did this, T1. Our Y value could be represented as T1 sine of 24.3. And I think you get the picture at this point. So likewise, this Y component over on T2 could be listed as T2 times sine 44.5. But those are not equal. They are applying a force. Together, they're holding this weight up in the air. So together, they're holding 24,240 pounds. The sum of the y components of our vectors must equal 24,240. So that is T1 sine of 24.3 plus T2, T2 sine of 44.5 equals 24,240. So what we have here is a system of equations. In fact, it's a linear system. It just is kind of ugly. But we got a lot of ways we could solve a system. If we could take this value and then the negative cosine 44.5 and the 0, this value, and this value, and put that into a 2 by 3 matrix, we could row reduced echelon form, or RREF this guy. And we got some technology that'll do that for us. And the nice thing about this, on our TIs at least, if we go into a matrix and enter this in a matrix, we don't have to figure out what cosine of 24.3 is and enter some approximate decimal. We can go straight into that matrix and represent our 2 by 3 and represent this as just cosine 24.3, provided your calculators are set in degrees, and then a negative cosine 44.5 and a 0. Second row, sine 24.3, sine 44.5, and a 24,240. And then we can RREF that, which I'm going to do in just a moment. I've got an answers button down at the bottom corner, and I'm not certain that's going to work, but I will reveal the answers in just a few seconds here. So you might, if you want to work through this to get the reward of having the correct answer, you may want to pause this, enter those values in your TI, and let's make certain that we're able to row reduce echelon form those to the same values. So this would be a good time to pause. Okay, welcome back, and we're going to see if my button works here. I don't believe it does. It didn't in a trial run, but I will still go ahead and reveal this. So it doesn't, as I expected. So let's take a look at what our solutions are. And I may be glad this happened anyway. Here are our solutions to this problem, 15,484.1 and 19,785.8. And maybe it'll be another time that we'll talk about what I did to produce this, where I can just enter some angles and enter a weight. This is such a classic problem, that this type of problem occurs so often that is the reason that I have a program like this that I created to do this for me. It's not something that I would just do one time. Not that type of problem. So there again, a very, very real world oriented problem. You want to do anything with suspension bridges. Obviously, here is a construction example. This is a type of problem that pops up just all sorts of times, and hope it was helpful for you. This can apply to many problems within our assignments, and certainly in your future endeavors, whether they be physics or calculus related. This could be very, very helpful process.